Hi everybody. Today we're going to work through several examples on, I believe it's page 53 and 54 of your workbook. So if you'll open that up now, take a second, and we're going to work through a few of these things instead of doing this in class. So tomorrow we'll practice this stuff. Now, we're going to talk about implicit differentiation today. And implicit derivatives are nothing more than an extension of the chain rule, and I'll show you what that means in just a minute. Now, this obviously wants us to graph, and you'll recognize the shape x squared plus y squared equals 9. Well, that's just simply a circle. So it'd be a circle of radius 3, and we just come over here and remember, just draw a circle of radius 3. Okay? Centered at the origin. Now it wants us to find the equation of the tangent line at 0, 3. Well, that would be right up there on the top. Right along here. Okay. And the slope, by looking at the graph, this is supposed to be a horizontal line, even though I didn't draw it very well. Okay. That, and what type of line is it? Of course, horizontal, and the equation then would be y equals 3. Okay, so what we're talking about this time is finding the derivatives and slopes of objects like circles or ellipses or hyperbolas or other objects that are no longer functions. And that's typically what we use implicit derivatives for, is finding slopes of things that are not functions. So what we could do is described here in this paragraph. We could solve for y equals this and then take the derivative with the chain rule and get something like this. Okay. Not quite. There is a 1/2 here as well. Okay. Sorry about that. So when x equals 0, dy dx is 0, and the slope of the tangent line is 3. However, it's a little bit easier method for doing that, and that's what's called implicit differentiation. Okay, and what implicit differentiation does is take each variable, the derivative of each component, with respect to x. Okay, so for instance, this would be 2x, and the chain rule would demand that we write dx dx. Okay, plus 2y, well, the variable we took derivative of is y, so behind that we write dy dx, and of course this equals 0. Now dx over dx is simply 1, so we really don't write it. But I wanted to show that to you, that we actually do that. It is chain rule component. It is the chain rule component of when you take the derivative of x, and the dy dx is the component when you take the derivative of y. Now the only problem with this is we actually have to find dy dx, which means we have to solve these things for dy dx. So even though we've taken the derivative, now we have the extra step of solving for dy dx. So I'm going to do that by first moving the 2x to that side through subtraction. Oops, darn it. So 2y dy dx is equal to negative 2x. Okay, then of course divide both sides and you get dy dx is equal to negative 2x over 2y. Those cancel out, so it's actually equal to negative x over y. Okay, now we want to remember that for the next question. Alright, the next question says, find dy dx for this. So notice this is the same exact thing. This x squared plus y squared equals 16. So when you take the derivative, you get the same result. Dy dx would still equal negative x over y, because this piece did not change and this is a constant. Now you can memorize that or just go ahead and solve it each time. It's up to you. But the derivative of x squared plus y squared will always be this. So now we want the slope at 0, 4. So what that means is we plug 0 in for x over 4. And what do we get? Well, we get 0 for a slope. And that's exactly what it's asking. Okay. Now notice this one's a little different. We want to find the derivative here. still dy dx, but since there's a y cubed, we must use implicit differentiation. So we follow the normal steps. Take the derivative here, that'd be 2 times 2x plus 1 to the first times 2, and that equals, well, we take the derivative of this, which is 6y squared, but since we took the derivative of y, we must write dy dx. Whenever this variable is not an x, you have to write this behind it. So now the only problem is we have not solved for dy dx. So that's what I'm going to do next. I'm going to go ahead and take these two, multiply them together, and distribute. Okay, so it's 4 times 2x plus 1 equals 6y squared dy dx. And then I'm going to distribute and divide by this at the same time. That's 8x plus 4 over 6y squared equals dy dx. Okay, and that's your answer here. Every implicit derivative has to be solved for dy dx. So you have to do whatever it takes to get there. So let's see another example. I'm jumping to example 6, which is a very similar question. So if you want to pause it for a moment and try to figure it out yourself, that would be cool. Pause, 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 pause. Okay, I'm back. So let's do it. Let's work it out. Remember, derivative of this side with the chain rule would give me 2 times 3x minus 1 to the first times 3. And that would equal 4y dy dx. All right? So once again, I'm going to multiply these together and distribute. That gives me 18x minus 6 over 4y, and that equals dy dx. Pretty straightforward algebra there while solving for dy dx, if you're careful. All right, let's try another. This one, very similar problem. Pause, try it yourself. Pause, try it yourself. All right, so derivative of this side is 2y. Oh, we took to the derivative of y, so we need to put a dy dx behind it. And that equals 2x plus 4. Well, that's not bad, because really all we have to do is divide by 2y. And I'm going to go ahead and simplify. Since I see a 2 here, a 2 here, and a 2 there, I can simplify this to x plus 2 over y. Not bad, is it? Well, let's see what the next example has to bring us. Well, this is not bad. So that's 1/3 x to the negative 2/3 plus 1/3 y to the negative 2/3. Oh, we took the derivative of y, so we write dy dx, and that equals 0. Okay, so once again, we're going to solve for dy dx. And notice here I've got a 1/3, a 1/3, and a 0 here, so I'm just going to cross those out. All right, I can divide those out very quickly and then subtract the x to the negative 2/3. So that gives me y to the negative 2/3 power dy dx equals x to the negative 2 over 3. And then, of course, we divide. And we get dy dx equals x to the negative 2/3 over y to the negative 2/3. Not bad. Almost done. Now we're getting a little more complicated here. So let's take a look. Derivative of this. See if you can figure it out yourself. La, 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 la. You paused and did it? Great. Let's check it out. 2y. It's a y, so we write dy dx. Minus 2, because it's that. Minus 3, derivative of y. Oh, that means we need a dy dx. Notice even though the y went away, we still have to write dy dx. And the derivative of this, of course, is 0. And that equals 0. So notice here, we have two dy dx terms. So we're going to keep those on this side, but move this to the other side. So we have 2y dy dx minus 3 dy dx equals 2. So what I'm going to do now is factor out a dy dx. Equals 2, and then divide both sides by this. And that will give me 2 over 2y minus 3. And that is your answer. Okay? Let's look at another. Very similar question. So give it a try. Pause it. Work it out. Great. Now let's try it out again. Very similar. You should get a very close, very similar result. Maybe not quite. So derivative of y is 2y dy dx. Minus 3 minus 2 dy dx. Remember, we took the derivative of y to get this. And that equals 0. So I'll move the 3. Okay. 2y dy dx minus 2 dy dx equals 3. Take out the dy dx. And then divide. And you're done. Okay, that wasn't so hard. Now some of the examples in between these have you filling in the coordinates. So take a minute and fill in those as you work this out, and I will be looking at that tomorrow to see that you did. Where you fill in the coordinate and find the slope. Very similar to how we did this question, where we found the derivative, plugged in the coordinate to find the actual slope. Okay, so take a few minutes, do that, and you'll be done. All right, great work.